We were talking about prime ideals. Let me recall a few things. This is such an important definition. I think it's not a bad idea to repeat a few things. So R is a commutative ring with identity 1. A proper ideal P in R is called a prime ideal if whenever A times B is in P, then either A is in P or B is in P for all elements A and B in the ring R. Maybe I'll also add one more definition here. An element P in R is called a prime element if round bracket P, meaning the ideal that it generates, is a prime ideal. I'm not sure if you want to call 0 a prime element, so let's say non-zero. Okay. So the prime, by this definition then, the prime elements in Z are exactly the prime numbers. And the prime elements in one variable polynomial ring over a field are exactly the irreducible polynomials. Yeah. Because this definition translates into saying, so P is a prime. Let's make some space. Is a prime element if whenever a product of two things is in the ideal P, that implies A is in the ideal P or B is in the ideal P for all A, B in R. Right? But what does A in the ideal P mean? It means I really need some more space here. What does A in P mean? Not A is in the ideal P if and only if A is P times something else. If and only if P divides A. That's what P divides A means, that A is a multiple of P. Yeah. So AB in P, this translates into if P divides AB, then P divides A, that's this statement, or P divides B for all AB in R. Make it then. So this is same as that. Which is the usual definition of a prime. All right. So we have a prime element and a notion of a prime ideal. And this is rather common. Whenever you apply a notion to an element that generally applies to an ideal, you're actually applying it to the principal ideal that the element generates. Okay. And we had these recognition principles. An ideal is a maximal ideal. If you quotient by it, you get a field. And you get a ideal is a prime ideal. If when you quotient by it, you get an integral domain. And both are actually if and only if. And since every field is definitely a domain, every maximal ideal is certainly a prime ideal. And then we gave some examples, and in particular that shows that the converse of this is not true in general. So the prime ideals in Z, for example, correspond to the prime numbers, those ideals, plus the zero ideal. Now these are all maximal ideals, but the zero ideal is not maximal. So here already you have a prime ideal that is not maximal. If you want something non-trivial, you can look at the two-variable polynomial ring over a field F. And there we checked, for example, that if you take the two-variable polynomial ring over a field F and quotient out by the ideal generated by one of the variables, like the ideal generated by X, then the quotient ring is isomorphic to polynomial ring in one variable again, which is a domain certainly. Polynomial ring in one variable is a domain. So the thing that you're quotienting by is a prime ideal. That's our recognition lemma on the left hand side that I just put a star against. So it's a prime ideal, but it's not a maximal ideal, because one way to say it is because that Fy is not a field. Since Fy is not a field. You could also say it directly without using this recognition principle. You could check by hand, verify that here is a strictly bigger ideal. That this is a strictly bigger ideal. The ideal generated by xy. But it's still strictly smaller than the whole ring. So for example, you can verify that y is not in this, but y is in this. So this is strictly bigger than that. This is strictly bigger than that. On the other hand, 1 is in R, but 1 is not in the ideal generated by xy. You can again verify that. So R is strictly bigger than the ideal. Okay, so this is more or less a pretty thorough review of where we were. I want to now focus on prime ideals in PID, because there nicer things happen. Okay, so PIDs are very special kind of rings. So like Z is a PID, one variable polynomial ring over the field is a PID. This is not a PID. Yeah, so here we have an ideal that is not principal. Not principal. Meaning you cannot generate this ideal with just one element. So in PIDs actually we can prove that the converse does hold. If R is a PID, let's write complete sentences. Let R be a PID and then a prime ideal in R is actually maximal. Let's try to see why. So I'll need some space. Let me get rid of these examples for now. So I want to show that primes in a PID are maximal ideals. So proof. Let P be a prime ideal. And I want to show that it's a maximal ideal. Remember what that means? That means that there is no ideal that is strictly bigger than P but strictly smaller than R. So let's take something that is in between P and R. Let Q be an ideal such that Q is between P and R. And what I need to show is that Q is either P or R, because there is cannot be something strictly in between. So now since R is a PID, you can find generators. This ideal is generated by some element, and this ideal is also generated by some element for some elements little p and little q in the ring. So what have I got then? So what I have is that the ideal generated by P is in the ideal generated by Q, and that's in R. So P in particular is in the ideal generated by P, so it's also in the ideal generated by Q. So P is a multiple of Q. Now P certainly divides P. So P divides QR. But now remember that this is a prime ideal. Or maybe let's just talk in terms of ideals. So QR is in the ideal generated by P, but that's a prime ideal. So either Q is in that ideal or R is in that ideal, since this is a prime ideal. Okay. Now let's take these two cases separately. So case 1, suppose Q is in the ideal generated by P. Then what? Then Q is P times something. So P is QR, which is PSR. And since R is a domain, you can cancel elements. P is non-zero. So maybe I should say non-zero here. Forgot that. So this is non-zero. So P is non-zero, so you can cancel P. So that tells you that RS is 1, so R is a unit. So that tells you that Q is actually PR inverse, which is in the ideal generated by P. But then if P is in the ideal generated by if Q is in the ideal generated by P, then Q, the ideal generated by Q, is a subset of the ideal generated by P. But we also have the other inclusion. So these ideals are the same. That is, Q in this case is just P. And let's take the case 2 quickly. Suppose that was case 2. R is in the ideal generated by P. Then what happens? Then R is P times something for some U in R. So again, you can write P equal to Q P U. So cancelling P again, you get Q U equal to 1. So 1 is in the ideal generated by Q, because 1 is a multiple of Q. But that's Q. So if 1 is in the ideal, then everything is in the ideal. So Q in this case is R. So what have we argued? We have argued that if Q is ideal, which is between P and R, then either Q is P or Q is R. So P is a maximal ideal.